Okay, welcome everybody to the last presentation of the afternoon. Thanks for staying all day and enjoying this new security mini session. We're excited to put it on for you. Today, we're going to talk about ways to leverage the Key Management Service for secure application design. Now, of course, there's lots of components to secure application design. Right? There's network security, there's identity and access management. You can even talk about the geographic location and physical security of things, but we're going to focus very much around the use of encryption and access control of encryption keys. We're going to talk about some best practices that we're seeing out there amongst our customers for how they're using KMS and how to take advantage of some of the features that we've implemented. I'm also going to talk in some detail about a new feature that we launched a couple months ago called Import Key. And then finally, something that we're really excited about is we've got a partner, Box, that's going to come and talk about how they are solving problems for their customers in the area of data security by leveraging AWS security services like Cloud HSM and KMS. So I'm going to start at a very high level. We'll get fairly deep, but I want to provide some context for how we're going to talk about some of the ideas inside this presentation. So I'm going to assume everybody here is familiar with the CIA model for security. Most people think about encryption as delivering on the confidentiality component, but it certainly plays a role in integrity. And of course, availability, making sure that not only your data, but the keys used to encrypt your data are highly available, is critical. So let's talk a little bit more about confidentiality. In terms of ensuring that only the right people get access to your data, with encryption, it's easy to reason about, well, I've got to make sure only the right person has the key. But when you're looking at systems where you're accessing the data remotely or accessing the keys remotely, you've got to think very deeply about access controls on those two independent resources. So for those of you who are familiar with identity and access management within AWS, you probably wrestle with the PARC model on a regular basis, defining which principals, whether they're users or roles, have access to which actions, which AWS APIs that affect which resources inside your account, which ARNs, and finally under which conditions. So access control is clearly critical. The act of encrypting or creating ciphertext certainly provides you protection for those who don't have the ability to get the key. When you use techniques like authenticated encryption, you can protect that data from modification. In many cases, it's easier to reason about the security of a single object like an encryption key than it is to reason about the security of lots of resources that may be protected under that key. And finally, I will continue to reinforce this idea that we believe it's critical to have independent access control for your encrypted data, the ciphertext, and the encryption keys. So while we do offer some transparent server-side encryption features in AWS, we think that all that really is doing is saying, well, if you've got permissions to the resource, we're just automatically going to get the keys and decrypt the data for you. And we give you an opportunity with KMS to define independent access control mechanisms on the keys to further scope down and tighten control. So, from an integrity standpoint, how do you make sure that the data that you put into a location, whether it be key or ciphertext, is the data that you get back? So you can use replication across independent systems. This will mitigate against corruption at the software layer or any type of risk to the server hardware itself that's storing your data. From a logical integrity standpoint, there's plenty of very common cryptographic techniques, as simple as checksums You can have complicated Mac implementations, and certainly using digital certificates. So the availability question is really one you need to decide for yourself. So if you think about the inverse, the unavailability of data, how much time can your users live without getting access to their sensitive data? Right? So you may, for example, have an application where the ciphertext is available, but the keys aren't, or vice versa. So you need to think about the union of the availability characteristics of those two services to define availability for your entire data set. The other issue on availability is latency. How much time does it take to retrieve a given object? When you think about the S3 case, S3 puts and gets, depending on the size of your file, the put might take, let's just say, an average of 500 milliseconds. So how much extra time is required to get the correct encryption keys, encrypt that data, write it to disk before you get a success response? Right? You need to account for that additional overhead. So I'm going to invent a sample application that has some security requirements, and we're going to walk through the C, the I, and the A implications for that, and how KMS and encryption in general across AWS could be used. So think about launching an instance. It's your own application code, and that instance needs to have the ability to talk to other remote servers or services. So we're talking about secrets that have to be deployed to the instance. And in many cases, these are going to be secrets that aren't used for talking to AWS services, because of course, something like EC2 roles already gives you rapidly rotating AWS credentials to talk to services. These could be credentials like I need to talk to a Mongo database, or a Cassandra database, or I've got some other third-party service that has a special set of credentials. How do I get these things down to an instance in a secure fashion? From a CIA standpoint, in terms of confidentiality, integrity, and availability, I'm going to assert a relatively simple set of requirements. First of all, your secrets can't be stored in plain text anywhere. You want to make sure the secrets are only decrypted on the instance that needs them, as opposed to perhaps decrypting them somewhere and then sending them down over a secure channel. From an integrity standpoint, as well as a durability of the secret, you need to make sure that these are replicated in multiple locations. And you want to make sure that the secret that you've defined isn't being changed underneath you without your knowledge. For the process of launching an instance, an application instance, typically this is going to be measured in seconds or perhaps even minutes, depending on how large the instance and the attached volume is. But the simple rule is, if the instance is launched and you have started to push code down to it, those secrets should also be available. And we'll arbitrarily say that this is going to be a relatively small instance, and we want this to take under a minute. So now, let's break these down individually. We said we don't want to store plain text secret on disk, and we don't want to decrypt the secret anywhere but the instance that you own. So what does this imply? What it implies is that you have to have encryption code running in your instance. Right? You cannot rely on a server-side encryption implementation, because if you're storing your secrets in a service that is doing server-side encryption, then that service is going to decrypt your secrets before it vends it to you. So if you stored your secrets in, say, S3, using S3 server-side encryption, S3 will decrypt before it then returns those secrets down to you over TLS. So the TLS session is absolutely secured with strong encryption. However, as a best practice, we think it's more useful to only decrypt that data locally inside your instance using application code that you control under a process ID that you own. So, what are your options on the client side? You could use the general AWS SDK and any of the KMS APIs to be able to pass some ciphertext blob and get a data encryption key. We also have some higher level SDKs, which are a little bit easier to use in various environments. For those of you who have used S3 a lot, you might be familiar with the S3 encryption client. The DynamoDB encryption client is also very useful to manage selective encryption on various tables, rows, or fields to optimistically and opportunistically encrypt only certain data to ensure you have high performance. So these are all client SDKs that get access to your underlying cryptographic provider on your system, but they still require you to supply a key provider. Now, of course, in this talk, we're talking about KMS as a key provider, and all of these are integrated with KMS, assuming you have a key in your account. You can also use any keys inside your existing key providers, whether they're managed by AWS or not. Okay? So let's talk a little bit about how the custom applications using the SDKs are doing encryption, because we think the idea of envelope encryption is very useful. And in fact, we use envelope encryption in all of the server-side encryption implementations across the, as of last week, 23 AWS services that offer server-side encryption. Why do we do envelope encryption? Well, we want to make sure that for every resource, and think of a resource as something that has an ARN, we have a unique data key. So that limits the blast radius of that data key to the specific resource. Whether it's a small 500K image that you're uploading to S3 or a 2 terabyte RDS database. That's an individual resource. We will provide an individual key. We also get a lot better performance because the encryption can happen locally when you have your plaintext that needs to be encrypted. You don't have to take all of your plaintext and make a network call to get it encrypted by the KMS service. Right? Instead, you get a key that can be passed down to your application and used by your application to do its work. And the only time you need to make a call to KMS is to get the ciphertext representation of that key decrypted the first time you need to use it. Okay? So, we had another requirement about keeping copies of ciphertext in multiple locations. So, using a redundant storage architecture makes a lot of sense. Within KMS, we actually store copies of your master keys in redundant storage locations, one of which happens to be S3, which is designed with 11 nines of durability. For your own applications, and what we see amongst our customers is a combination of S3 and sometimes Dynamo. Right? In many cases, Dynamo is attractive because much lower latencies. So if you need high volumes of keys and you're trying to minimize the impact of latency to your application, Dynamo might make sense, and you might use S3 as an archive. Okay? How do we ensure that secrets haven't changed since they were last used? So here, rather than having you try to manage a bunch of checksums or drive a MAC off of a secret, with KMS, we actually provide authenticated encryption by default. So whether you're submitting data directly to KMS, as long as it's under 4 kilobytes, or you're using envelope encryption and having data keys sent up and back to KMS, every encryption operation done within the service is using 256-bit AES keys under Galois counter mode. Now, I'm not going to go into the details of Galois counter mode, but one of the things that it does is it allows you to ensure that the integrity of the ciphertext is maintained between encrypts and decrypts. Now, one of the ways that we do this, we expose one of these parameters for integrity through a feature we call encryption context. So encryption context is an arbitrary string-string map that you can submit when you make what we call the data plane calls to KMS. So encrypt, generate data key, and there's two variants of that, decrypt, re-encrypt. Anytime you're using the key to create a ciphertext, you pass in this string-string pair. The next time you want to decrypt that ciphertext, you must also pass in the exact same pair. So this adds some additional security. It also enables you to use this string-string pair in policies. Why is that important? Because you might have a master key that's in use by a lot of different applications. Might be used by S3 for server-side encryption. You might have a master key that's also used by your applications because this master key represents maybe PHI for your US customers. So now what you want to do is ensure that the code paths that are coming to KMS and requesting use for that key are doing so in an expected fashion. If you implement encryption context in your application, you know that the decrypt operation should only happen on a ciphertext if it has this encryption context, and you can then map that back to the proper application. So that's why it's useful from an authorization standpoint. The more obvious reason for looking at using encryption context is in CloudTrail logs. So CloudTrail logs is our answer to prove to me that all my keys were used properly in ways that I expect. And what we do by default for all AWS services that integrate with KMS is we insert an encryption context that actually means something. This is the resource that you wanted to get encrypted. Now, the actual data key that encrypted that resource is hidden and transparent to you. But that data key itself was wrapped underneath the KMS master key. And you can see the key ID represented there. That's the generic identifier. But the encryption context now tells you why that master key was used. So you can start to build anomaly detection mechanisms. CloudTrail logs going to CloudWatch, creating events. You're looking for the absence of encryption context or some modification. That can trigger an alarm. It might even trigger a Lambda function. We just had a presentation in the other area where one of the security architects had a demo of how this could all work to, in many ways, have your secure application self-defend against code errors by your application developers or unauthorized users attempting to use your master keys inside KMS. So encryption context, very powerful concept. We have a blog on the AWS security blog that goes specifically around encryption context and all of its uses. Strongly recommend taking a look at that. So let's move on to the other requirements, which is if the instance can launch, the secret should be accessible, and it should happen within 1 minute. So clearly, we have KMS in every commercial region except China, which we're working on. You want to use KMS endpoints within the same region that your EC2 instances are running in. Remember that KMS is a regional service, so you don't choose which availability zone. We ensure that KMS is up and running and accessible from any availability zone. From a latency standpoint, this is something where, of course, your mileage may vary. We're working as hard as we can to bring down latencies for lots of our API calls. Again, you need to look and see what you need for the total end-to-end solution to either encrypt and write data or read and decrypt data and determine whether or not you can afford a call to KMS for each object, each data object that your application is processing, or whether you might want to reuse a data key inside your application in memory for 5, 10, 20, some number of objects. This reuse of a data key or caching data keys ends up being what we'll call a necessary evil in many cases because your application just can't afford the latency of making yet another network call. We strongly recommend you to think very hard about the reuse of data keys. That changes the blast radius of that key. It also changes the attack surface on that key. You should talk at length with your local security engineer to understand whether this is a safe mechanism. So a couple of the things that are useful when you're doing client-side development. We have a lot of customers that use the CLI. In the world of crypto, we deal with raw bytes. The CLI often deals with base64 encoding, so be aware of what encoding changes are happening. On the request rate side, so by default, we throttle the data plane operations, the encrypts, decrypts, at 100 requests per second. Now, we're in the process of trying to raise this default, and we can selectively raise this for you on an account-by-account basis. Reach out to us via the support ticket and create a limit increase request, and we'll get in touch with you to understand your use case. I want to talk about key aliases. So the ARN format of a KMS master key includes the 32-character GUID at the end. Not particularly human readable. We have a feature called KMS aliases where you can do effectively a symlink from a human readable string to a key ID. Now your application code can refer to the alias, and you can actually run the same code in different regions, but have a mapping of that alias to the regionally isolated KMS keys. So this might make deployment simpler as you go from region to region. Do be aware, however, that aliases are not supported inside policies. The reason for that is that the mapping of the alias can happen independently of the editing of the policy, and we don't want to allow escalation of privilege. Okay, so now let's dig in a little bit to the authorization logic for KMS. Like I said before, we think that the rules around how you determine who can use a key and under which conditions is ultimately the best set of tools that you can use to secure your data. So we start with what we call the key policy. So this is a policy that's actually attached to the key. For those of you familiar with S3 bucket policies, it's a similar concept, right? A key policy is not an IAM policy. It's important to remember. And all authorization starts with the key policy. There's another type of policy which we call a grant in KMS. And grants are a new construct that are really designed to be used programmatically, and they're designed to be used when you have certain resources that go from in use to at rest. And there is quite a bit of documentation on how grants are used within AWS service integrations, especially around EBS volumes, RDS databases, Redshift clusters. Right? What we are trying to accomplish with grants is to minimize any opportunity that AWS has in being able to use your KMS keys to decrypt something without your prior knowledge or authorization. And so in your application development, you might have cases where you need to temporarily give somebody access, or a lot of people access, to decrypt something, but then take it away. Right? And if you have some of these use cases and constantly editing and updating policy documents sounds onerous, take a look at KMS grants. Okay, so the other thing about KMS policies is you can delegate the ability for an IAM policy to be evaluated. So this is a little bit confusing. I've got a diagram here, hopefully you can read. So inside the KMS key policy, you can have a little statement that says, allow any IAM policies that refer to KMS keys, and this key in particular, to be evaluated. And we actually include that statement by default in all KMS key policies. If you edit that out, what that means is if you have a bunch of IAM users that you call admins, and you assume that they are going to go and administer KMS keys, they will quickly find that they cannot. And they say, well, wait a second, I am star. I'm the most powerful person in the account. What's going on here? And we did this on purpose because we feel that the KMS master key over time will be the most valuable piece of data that you store inside AWS. And we want to make sure you can look at a key policy and very easily understand exactly who has control over that key. So we enable you to define IAM policies because we know that most customers have been doing that and feel comfortable doing that. But for the very security conscious, it may be appropriate to actually remove that statement and only define administrators of a key inside the key policy itself. Okay. So now let's talk about key management options. So this is bubbling up a little bit. We've been focusing on KMS, but I want to make sure you understand how KMS gives you certain advantages, but could potentially come at a cost. So what I've done over the top is identify 4 categories: KMS, Cloud HSM, partner solutions, and whether they're delivered through Marketplace or you deploy them on your own, it's more or less the same, versus do-it-yourself. So if you think about where encryption keys are generated and stored and managed, with KMS we say, we are going to do this for you. We do have a new feature where we let you generate an import, and I'll talk about that later. But we handle all that part. With Cloud HSM, all this generation and storage is actually happening on a dedicated appliance that's designed to be very difficult to break into, so strong physical and logical security. With partner solutions, either the partner is hosting the key management, or it could be some other application that's running in a unique EC2 instance, typically inside your account. And certainly with do-it-yourself, it doesn't matter where it's running. Inside EC2, on-premise, you are in charge of both the physical and logical security of those keys. So where are the keys actually used? Who owns the code that is performing the encryption and decryption? With KMS, master keys, KMS owns it. We have to do the encryption and decryption operation. But inside your application where that data key is being used to encrypt your application secret, as an example, that's your code. With Cloud HSM, the keys themselves are used inside the device by code that is written by a third party and maintained by a third party. So that's what happens with the master key. The local data key, again, is running inside an application that you own. You'll notice that Cloud HSM does not integrate with other AWS services. And the reason for that is that in order for an AWS service to use Cloud HSM, that service and all of the AWS employees that manage that service have to have credentials to use your HSM. And we think that for customers who want the utmost in security, from a physical security standpoint using HSMs, it doesn't make a lot of sense for them to share credentials with an unknown number of service operators. So that's why Cloud HSM is really something that you've got to maintain on your own in terms of the keys as well as the client interfaces. So how do you do access control in these situations? With KMS, it's very similar to the way you do IAM. And we just talked about how keys have their own policy and they can delegate to IAM users. With Cloud HSM, this is very specific to the manufacturer of the HSM, in this case, Gemalto SafeNet. With partner solutions or do-it-yourself, again, this is completely independent of AWS authorization logic. Who's responsible for performance and scale? Only in the KMS example can you rely on us to provide the performance and scale that you need. Now, in some cases, if you need a ton of encryption operations and we can't give you the requests per second that you need, you might need to cache keys locally and manage that yourself. But in every other key management solution, you're in charge. And as I mentioned, the integration with AWS services, only with KMS do we have this integration, because only with KMS can we ensure that we minimize those service teams' ability to use your keys in some unauthorized fashion. We force those service teams to use the same access control policies and the same nouns and verbs for authorization that you have to use whenever you use any AWS service. So it's all very consistent and very tightly controlled. Finally, from a pricing model, in most cases, KMS is the only kind of pay-per-use. We're seeing a lot of changes in that area, especially with marketplace solutions. The model for the past 2 to 3 decades has been buy a specialized device and specialized hardware and run as many keys as it'll handle. We say that from a master key standpoint, you probably don't need a ton of keys. In fact, most customers tend to get by with something less than 10 to 20, unless they are themselves a service provider and they are trying to offer protection for their customers, in which case they can have thousands, if not tens of thousands. Okay, so let me talk a little bit about the import key model. So why did we build import key? Well, one of the problems that customers came to us with was, we have this KMS Create Key API, and that's great. And the feedback that I get, or the response that I get from the API is, here's a key ID, and here's the date it was created. But I have a couple of questions. How do I know that the key that was created that's inside the service is different than this guy's key or that guy's key? Prove to me that you are generating unique keys. Well, if you think about this, it's impossible to prove that because somebody would have to look at the keys and prove uniqueness. And as I said before with KMS, there is no code that will expose the plain text copy of your key to anyone. So we're stuck to some extent. So we wanted a way for customers to be responsible for the randomness of key generation. We also wanted to make sure customers could store a local copy. We offer 2 independent storage locations for master keys. KMS keys are the most durable thing in AWS. But it's theoretically possible that we could have some catastrophic event and lose your key, which would mean that your data is lost as well. So customers said, give me something that I can store somewhere else. So the way KMS Import Key works is you generate a key. We provide a secure way for you to import it into the service. And you can set an optional expiration time on the key that means that after that time expires, the key cannot be used anywhere inside AWS. And we enforce that at the heart of the KMS service. Once you import a key, you import it against a CMK key ID that's been created. So this imported key looks like any other key you would have been used to using inside KMS. Use it with S3, use it with Redshift, use it within your own applications, doesn't matter. Works exactly the same. And you can delete this key material, but re-import it under the same key ID at any time. So now you have a way to have a key available for encryption operations, remove it so that nobody, your users, AWS employees, nobody is going to be able to decrypt that data until you re-import the key material. Now, of course, getting keys out of existing systems, you want to make sure that those are secure systems. Most of our customers that want to use this feature are using some of the standard HSM providers and key management infrastructure providers like SafeNet, Gemalto, and Policy Security. So we are using standards-based approaches to let you take keys out of your existing key management infrastructure and import it into KMS. So let me just quickly go through what the workflow looks like here. You'll call a create key API, but set an optional parameter that says this origin of this key is external. That means we've got a key ID and all the metadata for a key, but there's actually no key. Then we're going to ask you to download a public key that is actually unique to this key ID. This is not one public key for all customers on the world or the region. This is actually unique to you and unique to this key. You then pass that public key into your key management infrastructure and tell it, send me back an encrypted copy of a 256-bit key. And this is a standard format that every HSM provider already provides natively. Now you've got an encrypted blob and you pass it under the Import Key API. We will decrypt it using the private portion of that blue RSA public key. And then we will take your key and encrypt it under our key hierarchy, copy it to multiple locations so that for the period that you want that key to be valid, we don't lose it. Okay? So, in summary, try to identify your confidentiality, integrity, availability requirements up front. In many cases, if you're working with partners or other customers as a service provider, you need to work with them. Use envelope encryption as a way to limit your blast radius. Encryption context. Can't reinforce this enough. This is super important to make sure you have a complete audit story as well as the best opportunity to scope down access control policies on the keys. If you need to be able to generate your own keys and store a copy, consider Import Key. And finally, as you build your applications, take a look at what's coming out the back end in CloudTrail. Verify that all the log events in there are actually telling you a story that will convince your auditors and your customers that it's what you need to do. Okay, at this point, I'm going to bring up Corey, and he's going to tell you about how Box is trying to solve this problem of data protection and security for their customers. Okay, thank you.
Hello, everyone. My name is Corey Minkovich. I'm a staff software engineer at Box, and I'm going to be presenting Box KeySafe, or how KMS saved us from managing HSMs. A lot of you already know what Box does, but Box is a modern content management platform that transforms how organizations work and collaborate to achieve results faster. I like to think of Box as the heart of the modern enterprise application. By centralizing where your content's stored, we provide the same security and compliance to every single application. Take, for example, DocuSign and Salesforce. When they both store their content with Box, you know they meet the exact same security requirements. Let's take a look at a specific example of how this works. Here is a highly regulated industry, the healthcare industry. And they want to make a simple application for their customers. Instead of having to reinvent the wheel, they can leverage Box to meet their compliance requirements. And by utilizing the Box platform, they can get easy content management, collaboration, and security delivered to their customers while knowing they meet all the HIPAA requirements. But other industries are even more regulated and require the company to manage their own encryption. So historically, customer-managed encryption has been pretty hard. Your choice has been between client-side agents that sit on your computer and basically wrap the Box sync app. And every time you want to store a file, it encrypts it before it gets sent to Box. And every time you download it, it gets decrypted before it arrives at your computer. But the problem is this breaks the mobile experience and this breaks the web app. Another solution is proxy-based encryption, where it's basically a VPN that sits in front of Box, where customers upload, and as long as they're connected to the VPN, it'll encrypt it, and when they're accessing that content, it'll get decrypted again. But the problem is this breaks collaboration. Imagine if you're trying to share a document with a vendor and you send them an invoice. They're not going to be connected to the same VPN. They're not going to be able to access that content. A third interesting solution is API after upload. If you can selectively classify the documents you have that need additional security, what you can do is have an independent process override those files with encrypted versions. But again, you never know what's actually going to be encrypted, and if the classification doesn't really work, you're going to run into problems with collaboration. So there's a couple drawbacks to these historic solutions. They decrease productivity and ease of use by breaking file preview and the mobile access. And nowadays, most access to content, people just expect the mobile experience to be working. They actually decrease overall security by breaking antivirus. If we can't scan the content, then we can't provide antivirus on it. They break governance controls because e-discovery is based on text search. And if we can't do text search over the content, then e-discovery can't work. But the bigger problem is the incentivization for shadow IT. If you're going to go on a plane ride and you need to edit your PowerPoint, you're most likely going to download it and maybe even email it to yourself to your personal Gmail account just so you know you have access because you don't trust the historic solutions. So let me introduce Box KeySafe and how we allow customers to manage their own encryption. I'm going to go through a 4-step process of how a file gets uploaded to Box and encrypted and how we interact with a customer's KMS instance or Cloud HSM instance. So step one, a file is uploaded, and as Ken pointed out, envelope encryption is the right solution for especially arbitrary sized files. So we create a brand new data encryption key for that file. We encrypt it once a box, and then it gets sent over to either a KMS or Cloud HSM. This creates an audit trail that the customer sees. And what you see is a clear separation of encryption responsibilities. And instead of modifying the front door and damaging the user experience, what we've created is a seamless backend integration that allows the customer to maintain the ultimate control over their data. Let's dive a little bit deeper to see how encryption works at Box. And we're going to go in a comparison of standard encryption, and if you add Cloud HSM, and if you add KMS, and how those differ between each other. So the native Box encryption is vanilla envelope encryption, as I like to call it. A file gets uploaded, a unique data encryption key is generated. That file is encrypted with that data encryption key and stored. Then the data encryption key itself is encrypted with the Box key encryption key, and that's stored. But we wanted to allow the customer to control part of this flow, to have the ultimate on-off button. So what we've done in the Cloud HSM case is we still upload a file, create a unique data encryption key, and still encrypt it once. But then we add a second layer of encryption using, in this case, a Gemalto HSM. So we take that singly encrypted data encryption key and send it to the Gemalto HSM. That creates a log that can go to the customer's Splunk instance. And then if they need to back up that HSM, they can create a backup HSM and instantiate it into as many regions as they need. Now, managing HSMs has historically been quite difficult, and a lot of customers are not at the right size to manage a whole group of HSMs. So what we've realized is the way that we use the HSMs, KMS is a perfect fit to be swapped out. So we send the singly encrypted key to KMS for an additional layer of encryption, along with audit parameters. And here, there's a cloud trail to generate these audit logs that feed into the customer. And with the new key importation feature, they could also use their backup HSM to import into KMS. Now, let's compare and contrast from Box point of view, Cloud HSM and KMS. And before I start, there's a lot of benefits to Cloud HSM. You get level 2 FIPS validation, and FIPS validation for hardware is quite difficult. You also get single tenancy, where that HSM belongs to you, and you know how many requests per second it can handle. So KMS, as Ken said, the default rate is 100, but that can be increased much larger than that, and is for a lot of customers. Cloud HSM, on the other hand, is quite slow, especially with audit logging. There's special patches you can apply, but most customers end up running a cluster of 3 to 6 HSMs. The biggest difference is kind of the reliability, where AWS is managing KMS, of scaling, of making sure that it's up, while Cloud HSMs have to be managed by the customer. That means they must manage patching, they must manage high availability. And then, as from our side, we have to support every HSM version, and different versions require different client library, so it becomes much harder for us. Let me give you an anecdote to kind of show the difference between the two. We recently had to update the HSM client library, the Java library, so we went to the Gemalto support site. We searched for their library. We found a library that seemed to be newer. We downloaded it. It's password protected, so after a few emails back and forth, we got a password. We decrypted it. We got a Windows binary, so we could accept a EULA. We then accepted it on a Windows VM. Then that gave us a tar, and inside of that tar, we finally got our jar. So, and I'll go just a little bit further about our architecture and how we communicate to these HSMs to maintain high availability and the performance expectation of people using Box. Because people don't want the performance to be degraded just because they're adding extra security. So at Box, we have something called the Key Encryption Decryption Service. And I want to show how we communicate with KMS and Cloud HSM. What we do for each HSM customer is we spin up a new HSM connector. And this is because the Gemalto library uses environment variables for configuration. What it also does is it provides isolation between different customers. If there's a crash and takes out the JVM, it only won't impact more than one customer. Then, secondly, inside each one of these HSM connectors, we talk to each HSM individually. That way, if one of them locks up, we can quickly fall back to another one without the customer realizing it. If you compare this to KMS, it's just a RESTful call using the SDK. So let's dive a little bit deeper into the KMS code. So health checking is one of the most crucial parts, at least for Box, of knowing if the customer's KMS is accessible and we can use it. This is a snippet of Scala code, but what it basically does is it does a described key on the KMS we're trying to talk to, and then it checks if the key is enabled, and if we can perform encrypts and decrypts. The other thing we use is CloudTrail logging. So in this case, we want to send a set of 4 things that will want to appear and an annotation to CloudTrail. For example, we send the request ID, an object ID we're trying to access, the enterprise ID requesting it, and the user ID. We convert that to JSON, and we put it in a header called the CloudTrail annotation. What happens is when Amazon gets this request, it takes that header, and when you're looking at your CloudTrail logs, you'll just see this JSON expanded out. Now, there have been some challenges with using KMS. There's 2 specific challenges that I wanted to talk about. One of them is key rotation. So natively, KMS supports yearly rotation, but some customers want quarterly rotation, and the only way to do that is to create additional master keys, and that can be really cumbersome. Furthermore, some compliance schemes require that the data encryption keys be re-encrypted after the key has been rotated. The issue with these bulk rekey operations is that only CloudTrail knows if a key rotation has happened. As of now, there's no way to tell if an encrypted blob was created before or after the key rotation. And the only safe way for us is just to go and re-encrypt all the data keys over that period. The second concern that some customers have is key availability, and Ken has addressed that a little bit with key import. KMS keys are regionally isolated. It has high availability within the region, but some customers wanted more control, but luckily they can use key import. The one problem with key import is that it breaks simple key rotation. You don't get a simple checkbox that says rotate this key yearly, and then you have to create multiple master keys. And this is not easy to automate on our side or on the customer side. Okay, let me summarize KeySafe for you. By integrating with AWS, Cloud HSM, and KMS, this has allowed Box to give the customer a guaranteed audit trail, the ultimate access control, and it was easy to incorporate into envelope encryption. At Box, we don't cache data keys, and we have third-party auditors that come and audit our code to verify this, to give the customer the reassurance. This did have some trade-offs. We have a minor latency increase because we have to call these services. And it did increase the availability surface area because you are talking to 2 additional services. But these trade-offs are much more palatable to the end user when compared to customer-managed encryption, the historic way of doing it. Thank you very much. If you want to email me or the team, just send an email to keds@box. And remember to complete your evaluations. If there are any questions, there's 2 microphones in this room, and Ken can come up and answer any questions you might have.